tools for the SPICE spectrometer and is focused on the study of dynamical solar atmosphere and fusion plasmas. So whenever you're ready, take it away.
Okay. Okay, so can you all hear me properly? Can you hear me properly?
Yes, thanks.
Okay, fine. Okay, so I can start then. Okay, so thank you for inviting me. And today, actually, I would like to explore in the interdisciplinary link between two different environments that seems quite far away from each other, but actually they have got lots of things in common. And these are the solar context, solar environment, solar physics, and the fusion, control the fusion environment, specifically the solar atmosphere, and a device, a part actually of device, which is called token magnetosphere. And I want to actually talk about some plasma diagnostic and the spectroscopic technique that we can share between these two fields. This is a work that actually I started to do after my PhD, together with Professor Hugh Summers and Dr. Martin Amulan and Stuart Anderson and James Harrison. They are all working at the current Center for Fusion Energy. And for the solar part, actually, I collaborated with Professor Jerry Doyle from AMA Observatory, especially on the transient modeling for solar atmosphere. So, first of all, I'll just give you an introduction, a very general introduction. As we know that in the emission in general, the emission of photons, so the spectra that we can see from a source, they are the signature. Actually, I like to call them fingerprints of the plasma from which of the plasma parameters from the source that give this emission. So so this emission line, so this spectrum, allow us to infer the physical and chemical features of the emitting source. This is true for both astrophysical plasmas and laboratory plasmas. So astrophysical plasma that can range from this deep space to actually the sun, which is our star, and in this case, the radiation in practice is the only avenue open to us. So the only thing we have to explore and to understand the characteristics of the source. Another now, actually, there are very new missions like Parker Solar Probe and Solar Orbiter that are very close to the sun. So they can actually collect particles at the spacecraft level, like protons, heavy ion, electrons, but they are not still at the source. So the only thing we have in practice is radiation. For laboratory plasma, we are to be luckier because we got also other diagnostics like probes or particle sample, something that you can put inside the device actually to see the status of the plasma. But even in that case, the radiation is observing the radiation is one of the limited number of methods that we can use to study the plasma inside this kind of devices. So for both environment, the analysis of the plasma from observation of the spectra, so the spectral line that we see on the mission, is a very powerful tool to actually gain physical insights and understand how we manage to carry on. So, okay. So I don't know, I carry on talking, so I don't know how far actually.
You finished this slide, but we didn't get to see the next one.
Okay. I would like to give a brief summary of the two environments. So starting from the sun, this is the solar domain, which is called the solar domain. And here I just show a nice video that hopefully it will work. Yeah. It actually doesn't, but yeah, it should work. So just coming back to the previous one. hopefully reappear again. I'm sorry, I don't know what happened to my computer today.
Yeah, we can
So
see.
again, so it doesn't matter if the video is working or not. However, this is a video that show actually how the plasma is dynamic when we look at this through the extreme ultraviolet emission from the upper atmosphere. And these are all images that are taken from the Atmospheric Image Assembly (AIA) on board of Solar Dynamics Observatory (STO). In particular, you saw the red one was the helium-2 304 angstrom passband, which showed the chromosphere and still very active. And this yellow one that you see here is the iron 9 171 angstrom, which will show the upper transition region, actually the corona. And as you can see here, the sun appeared very, very active, and this is an example of actually ejection of matter from the limb here. And this video will actually end up with a very nice flare from the bottom right of the sun, which you see in a little while. And all these loop and dynamic part of the sun actually show that the solar atmosphere is really, really very dynamic. So here it is the big flare. So after this video, actually, I just wanted to give you a very quick overview of the solar atmosphere. You probably know very well, and still using the STO AIA passbands. STO AIA has got 10 passbands, but I just selected 4 to actually show the 4 layers of the solar atmosphere that we see. These are all observations from 2017, September 2017, after midnight. And we see the first one, the photosphere. This is actually what we see from the Earth. This is shown here through the continuum, 1,700 angstrom, and the temperature is quite low actually compared to the upper layers of the solar atmosphere. So only 4,500 Kelvin with high density of 10 to the 17 centimeter to the -3. And then the layer above the photosphere is the chromosphere, which is what you actually saw in the video before. Emission, this is emission from helium-2 304 angstrom, where the temperature is increasing. The chromosphere is actually a layer of about 2,000 kilometers thick, and you can see here the supergranulation actually, and the temperature is increasing compared to the photosphere up to 10 to the 4 Kelvin, while the density is decreasing, reaching actually 10 to the 11 roughly centimeter to the -2. And then the last layer will be the corona, but between the corona and the chromosphere we got a very, very thin layer, is only about 200 kilometers thick. And in this layer, actually, a lot of things happen because we got an increase of the temperature from 10 to the 4 to actually 1,000,000 Kelvin, while the density is dropping down from 10 to the 11 up to 10 to the 8 centimeter to the -3. And this is the other line actually that you saw in the video before. And finally, we got the most extended layer of the solar atmosphere, which is called the corona, is the one that reaches actually the interplanetary space up to the Earth and the planets. And here it is shown with the passband of iron 1894 angstrom, which reach a temperature of 6, can reach out to 10 to the 6, 10 to the 7 Kelvin, and the density is dropping to the 10 to the 8 centimeter to the -3. And actually, at 1 solar radii, it can reach 10 to the 6 centimeter to the -3. And while the temperature, which is so high at 1 radii, can be reduced by up to actually 10 to the 5 Kelvin when reach 1 AU. And this is the solar context. Now we move into the fusion context. And here I show another video. And this is actually the emission. This is a typical pulse emission from inside MAST is a mega ampere spherical tokamak experiment in the UK, close to Oxford. MAST actually was finished to build up in 1999 and was generated the first plasma in 2000. So it was working from 2000 to 2013. In fact, this video comes from 2007. But after that, actually, it was shut down, but it was rebuilt to improve all the characteristics. And now it's still in operation, but it's called MAST Upgrade. And the MAST is actually a tokamak. And a tokamak is a device which consists of a vacuum vessel, which you can see here in this picture, and confine the plasma in this vacuum vessel, which has actually a ring shape, a torus shape. And to create a plasma, there is a puffing of deuterium or tritium, which is put into this vacuum vessel, and the high voltage create plasma, splitting the neutral gas. And this plasma is held and shaped by a very high magnetic field. And for the video that you saw just before, the MAST, this magnetic field is 0.5 Tesla, while for the JET, which is this figure that you see here, the Joint European Torus, the magnetic field is up to 4 Tesla, so it's quite high. And actually, the JET is at the moment, is currently the largest tokamak operating. In fact, if we actually need to talk about actually dimension, the MAST that was just the one that we saw before is just 8 meters square, while JET is already 80 meters square, and give a power of 16 megawatts. And this is in the roadmap towards the fusion. In fact, the next one, which is they are now building up, is ITER, and this is much bigger. 800 meters square, which are higher power, 500 megawatts. And they are building this in Cadarache, which is in the South France, in Europe, close to Marseille. And it will have actually quite in a good shape. It's in a good shape. They will have the first plasma into 2020-25. And after ITER, the next design will be the very first interface between an experiment, which is JET and ITER, that just experiment on Earth, and the first fusion power station. In fact, will be much larger, and the power that we generate will be over 2,000 megawatts, so really high. However, there is also another thing to say here. When the plasma is generated inside this tokamak, inside this ring, this torus, then we'll have an excess of heat, which is actually exhausted using what is called divertor. The divertor is the bottom part of a tokamak, and I would like to concentrate on that because this is what extracts the heat and ash. What we call P out. And if you look, actually, JET was very small, but if you look, for example, ITER and the demo, the power out, so this exhaust is very large, is 10 megawatt or 300 of 300, 400 megawatts. And if you think, for example, that an average UK home use of energy is around 4,000 kilowatts, so this is already much bigger, so it's very big. And so we need something, which is actually the divertor, that extract this heat and ash and try to actually protect the wall from this thermal rod, which is actually this divertor. So now, carry on. How can we put together these two fields? So, and we can interpret. And what we say is that atomic physics will provide us the link to interpret the spectra in terms of the properties of the source from which they arise. That can be temperature, the temperature, the density of the compositions, of the status of the source of the plasma, if it is in equilibrium or transient. So if you look at this plot, in the x-axis we got the wavelength range, in the y-axis we got the temperature, and so all these points here are the ion, and the line where the lines derived produced by different ions at different ionization stage are produced. And at the top, you can see I put just three of the space-borne spectrometer, ACE, CDS, and SUMER. So ACE on board in order, CDS and SUMER still on board also, even if they're not operating anymore. And this is the wavelength range. So all the ion, the lines that can see this instrumentation. And actually now we got SPICE on board Solar Orbiter will be around this range, even if it's not shown in this picture. Is about 700 and 1,000 angstrom, and we'll have also IRIS. The first band is within this range, and the other band will be out of this plot. And at the top, you can see all these KT, KT1, 4, and so on, which are the spectrometer that are installed at a jet to look at the plasma within the jet device. On the right, we can relate this plot to what happened in the sun and in an example tokamak, which I put jet here. As temperature rise, we see the different layers of the solar atmosphere, some from the corona, from the chromosphere, upper chromosphere, lower transition region, where we see actually the helium, neutral helium, single ionized, and silicon 1 and 2, carbon 2, 3, and then up to the transition region, where we see ion with high ionization stages and the corona. And the opposite way is for actually the tokamak, where we see emission for the scrape-off layer, which is a layer where it's a layer between open and closed magnetic field line. It's called separatrix, and going down into the diverter. And I concentrate on the diverter because it's where the temperature is dropping down, so it's a little bit closer to what we observe actually in the solar atmosphere, and the density is also dropping down because the density within a tokamak is very, very high. It's much higher than the one we observe in the solar atmosphere. While in the diverters start to drop to 10 to the 14 up to 10 to the 12, 11 centimeter to the -3. So it's much closer to what we see actually in the solar atmosphere. And this is very important because these similarities between the astrophysical laboratory plasma, specifically solar atmosphere and tokamak diverter, will enable us to develop a common modeling approach to study the plasma. So then carry on. These are actually the motivation. So and from both experiments, measurements, observation point of view, and theory point of view. From the observation, we know that we got new spaceborne instrumentation like IRIS, and we got SPICE on board Solar Orbiter, which has been launched last year in February. And this instrumentation allow observation to up to actually a relative dense upper chromosphere lower transition region. So that's quite important. And also are oriented to dynamic conditions. For example, we want to watch flare. And from the fusion point of view, we have got the development that require actually advanced modeling of heavier species as tungsten for the ITER, for demo, and for new step that will be actually is designed now in the UK for the wall. But also need to understand the dynamic behavior light elements like helium and neon and argon observed in the diverter, in the Max Super X diverter. From the theoretical point of view, we saw that there were various studies which were confirming that the use of a zero density approach or oversimplification of theoretical atomic modeling could lead to misinterpretation when we want to compare measurements and theory. And so we need, so it is required obviously a continuous development also from the theory point of view in order to update and have appropriate atomic modeling population, which include the finite density and also the non-equilibrium effect when needed. And so obviously we know that in most cases, but not always, but in most cases in the solar domain, it is common to assume that the observed solar atmosphere has a plasma that is optically thin, which is zero density and steady state. But there are lots of evidence that this is not always the case. Here I just put three examples on what I worked actually during my PhD and actually also after. And the first is that the effect of final density in the population distribution cannot be really ignored when the observation are extended down to the upper chromosphere's lower transition region. So exactly what Iris and Spice will are observing actually. This is the case, for example, of the announcement of helium line, neutral helium lines, which can be partially explained by final density modeling and partially explained by the non-equilibrium effects. And the second is the truncation of atomic population structure to a set of low levels, which is done quite often in the coronal model, can lead to the misinterpretation. I will show you an example later of this. And finally, the analysis of dynamic plasmas, so flare, obviously tokamak divertor, because that is also very dynamic, cannot assume equilibriumization balance when we want to actually reconstruct the intensity. So given all of that, we need to move into a final density modeling. And this is actually approached by the generalized collisional radiative model, which is described by Summers et al. 2006 paper. And this model will handle at the same time comprehensively the issue of density, the level truncation, and also the metastable states, which actually can be treated as ground level when the density is not zero anymore. And this approach will allow to actually reconstruct and model the observed intensity in a quite large range of plasma regimes, so from the solar atmosphere to actually diffusion devices. And now this modeling is fully developed within the Atomic Data Analysis Structure database. Here I give you the website, but there is also an open website. It's called OpenADAS, where you can actually download the data, very similar as Chianti does. So they're open to everyone. There is also a program there to read them. And this model has been developed Aptenian, and I have extended this to silicon during my PhD thesis, and now is also extended to argon. So here is just actually this plot just show visually the final density modeling and where it can be used. So where in the plasma regime, so where actually it is good to use a coronal modeling when actually it is better to use a final density modeling, so collision radiative, generalized collision radiative. Obviously, this case is more appropriate maybe for fusion because carbon-2 actually is inserted in the fusion plasma. And here on the right, I show actually a schematic of the levels of the carbon-2 plus. This is the ground level in a single spin system, and this is the metastable level. We actually does not contribute when we actually use a zero density model. And here, this plot shows the ionization rate coefficient, so which is one of the coefficients that is needed to build up the emissivity of a line, so the intensity. And this is then resolved in the case of the ground level and metastable. What actually is important in this picture is mostly the regime. So this density, and here is less than 10 to the 10, is where the coronal model can work, especially here when actually the result case is exactly the same behavior as the ground level. So it is good and appropriate to use the coronal modeling. But as soon as we go up, so already in the chromosphere transition region, also flare, so just 10 to, even from 10 to the 8, 10 to the 9, 10 to the 10, then we see that actually a final density model will be more appropriate, and also definitely in the tokamak. So carry on. Actually, I would like to concentrate now on the spectroscopic technique and analysis. Because we got quite a lot of progress of fundamental atomic calculation. This is seen also in the new actually Chianti version, which has lots of new fundamental data, and the same fundamental data are shared between Chianti and others. The modeling, the only difference is the modeling. One used the current model and others use the full final density modeling. And so because of this improvement, this can allow us to improve and update the diagnostic techniques for deriving the property of emitting plasmas. And here I just put two examples, which are the most common example used in solar physics, and to derive the temperature and density of the plasma, and also to derive the status of the plasma. And these are the differential emission measure of emission measure and the line ratio from the same ions. The differential emission measure is derived by actually this big equation, where we got here the intensity, the observed intensity, the A Z, which is the abundance relative to hydrogen. And in this integral, we got two parts. One is all the theoretical, which include all the theoretical model, all the atomic model, and the other part be what we call actually differential emission measure, and it is derived by inverting this equation. So what we need to know is actually the atomic model behind, and this one is called contribution functions, depend on temperature, electron density, and it consists of two main parts. One part, which is called photon emissivity coefficients, and take into account all the contribution due to the excited population. And the other part, which is called fractional abundances or ionization balance, and which take into account all the ionized, so all the ionization contribution to the emission, to the line that we actually observe. In this case, this fractional abundances is calculated in equilibrium. And a simplification of all these big formulas given when we use a line ratio from the same ions. So the ratio between the two intensities will be simplified to actually only the ratio between the excited population, the upper level actually population from which the two lines arise. And now I'll give you an example actually of line ratio and how you can deduce, for example, the temperature, and is given in this next slide. Actually, this slide show actually two actually main important message. One is actually how to derive the temperature from a line ratio, but it's something quite common. So the lines that we go here show the ratio between two lines. In this case, we got the oxygen 4. Oxygen 4 is observed by Sumer, CDS, and ACE. These are observations that I use in my thesis, in my PhD thesis in 2009. And you can see that lots of lines from oxygen 4 are observed. And in particular, there are two lines, one from Sumer, 787 angstrom, and one from another ACE to 179.9 angstrom. The ratio between these two lines will give a good diagnostic of temperature. And so to derive the diagnostic temperature, we need to compare obviously the theoretical values with the observation, which are these points. And this orange line, the upper line, from where we derive very, very high value of temperature, which actually seem to lead us to a non-equilibrium properties of that specific plasma, are derived from a very old version of Chianti, version 6. Now we go actually much newer, I think, or 8, maybe more than that. And the problem there was that there was a big truncation in the atomic data. In fact, if you see these two lines, they are produced from this is the upper level for the 787, and this is the upper level for the 279. But these upper levels, it comes from N equals 3. So for this data set, for the Chianti, all the version Chianti data set, all the levels with N equals 4 and N equals 5 were completely truncated and cutted. And so they were not actually populating properly the upper level from which actually the line, the another line was actually rising. And this was leading to underestimating the population, so overestimating the ratio. And obviously, here go a misinterpretation of what you get from that. So when you add all this missing level in the modeling, all the ratio is going down. It's the green line. It's called revised data. And obviously, all the temperature is going down, much closer to equilibrium for oxygen 4. And this is proved also for the new calculation done later on from Agar-Belkinen and Lien et al. So this is just an example to show how important is the completeness of atomic data. So carry on now. I'm calling from now up to the end of the talk. I would like to actually concentrate on the transient modeling. A short example of this on the solar side and on the fusion side. So from the atomic point of view, we can define a transient time described by McWriter 1965 paper as a time to reach the steady state equilibrium. So when the ionization are equals to recombinations. And here is described by this formula, where S is the ionization rate coefficient, and alpha is the recombination rate coefficient, and Ne is the electron temperature. So non-equilibrium occurs when a plasma electron temperature or density change on time scale shorter, so much quicker than the ionization and recombination time scale, which is called transient time, given by this equation. And generally, the ionization and recombination time scale are of the order of 100 seconds. So, for example, if you think about a flare, we will have change in temperature density quicker than 100 seconds. It can be also seconds or can be 10 seconds. So in that case, for example, the plasma is not in equilibrium anymore. And so if it's not in equilibrium, you saw the question before that was describing the intensity, and there was the fractional abundance is calculated in equilibrium. So when this is equal to 0. But if we don't have equilibrium, this is not equal to 0 anymore. And so this long equation, where we got the ionization and recombination coefficient in it, will need to be solved using an integral, a proper integral. And once we got the solution, this will be put into our contribution function, which contain everything related to the theoretical modeling, and which will depend not only from electron temperature by electron temperature and density, but also by the time. And the dependence of the time is essentially in the ionization fractional abundance, the fractional abundances, and this is because the PC, the photon emissivity coefficient, so the excitation part, has got a scale of the order of 10 to the -4, -5, much quicker the change of electron temperature and density in the plasma. So now I would like to show you how to apply this model to two cases applied to the solar atmosphere. So one case was a work that I've done with Professor J. Doyle. It's a case of flare that has been observed long time ago, so in 1980, during the solar maximum emission by the UV spectrometer and polarimeter, and at the same time by the hard X-ray burst. And here we describe a method to actually derive the electron temperature and density using a transient modeling. So in this first plot on the left, you see the oxygen 5 and 1371 angstrom. So this is the intensity of this line as function of time. And you can see the burst. Each burst corresponds to hard X-ray burst, which eat up the plasma there. So you can see the, at the foot point of the loop, and you can see the emission of oxygen 5. And each of these bursts has been actually modeled as an independent entity and fitted to derive the peak and the decay time, and modeled using the transient modeling. So the comparison between the peak calculated by the modeling and the fit and the decay time is shown in this plot, where we go density and temperature. So the crossing, this is an example of just two bursts, burst 3 and burst 7, will give us the values of electron temperature and electron density, which you can see in these two plots on the right. So we got the electron temperature for each burst, which is almost constant, and the electron density, which rise up in the peak, at the peak of this flare, and going down afterwards. The second example is much more recent, and is how to actually diagnose a transient ionization from the observation. So it's the opposite now. And here we see an observations from IRIS of April 2014. It is the case, observation specifically two lines, silicon 4 are 1394 angstrom, which is a permitted line, so it could be a very strong line, and oxygen 4 are 1401 angstrom, which is actually, if you see here, you got two different spin systems, so it's an intercombination line, so it's a forbidden line. And these two lines are observed by IRIS. Here you can see actually, you can see the context. This is a SDO image, and the region observed is a very active region, very close to the limb here. IRIS has got a context, IRIS context image. This is the filter of carbon to actually 1330. So, okay, I'm still here. Sorry, I was thinking that.
So it looks like we lost you again. Let's give it a minute for her to reconnect if there's a connection issue.
I lost the connection again. I don't know really why. I'm sorry. I'll try to share again. Hopefully, okay. Can you see the slide?
Yes.
Okay. See if we manage to carry on. Okay. So, so did you actually? I don't know. Again, I don't know when up to when you managed to listen to me. So can I just carry on from this slide?
Yeah, I think the last thing you were talking about the IRIS context image being the carbon 2.
Okay, perfect. Okay, so it was just at the end. Perfect. So on this slit actually is take so that's the context image, and then there is a slit here, which make a raster 8 plus times 2 second slit times 8 raster position. So with a cadence for each raster of 1031 seconds and 155 raster position. So what I've done here was to select two parts of this region. So the active region, actually calling flaring region, and the quiet sun region, and calculate the intensity of these, derive the intensity from the observation, and make the ratio between the intensity from the active part and the quiet part. What we can see, as shown that from this plot, this is the ratio between the active region and the quiet sun region. For the silicon 4 after the oxygen 4, and the silicon 4 is these black points, and the oxygen 4 these red points. As you can see for these plots, the silicon 4 intensities in the flaring region is enhanced by a factor from 7 to actually up to 23 compared to the quieter region. While this enhancement is not really evident in the oxygen 4, is much less, including also all the measurement error. So what this actually could be an indication that here we have something different from equilibriumization. And so what we've done here, just come to the theory. Oh, again. I'm still there. Okay, I'm still. Just take an hydrodynamic model, 1D loop model, which a code which is called Argos to make this hydrodynamic simulation. So the loop length. So we try to simulate a small flare with this hydrodynamic model with a loop of about 80 megameters, and putting an impulsive heating with a pulse cadence of 1/4 of the loop cooling time, and giving an energy of 10 to 24 erg. Doing this simulation, obviously this is just an extractor one time, and this is and also including in this simulation the transient ionization, and this is actually the ratio. These two will show the ratio between transient ionization and ionization at equilibrium for the silicon 4 and the oxygen 4 lines, as function as of the loop length. So these two that you see are the foot point. You see that the behavior of the two lines is very different. So the silicon 4 is enhanced by a factor 4 or 10, while the oxygen 4 just by a factor 3. And here you see all the questions that actually show you how to compare the observed ratio with the model ratio. What we can get here, at least qualitatively, is that the two lines have got a very different response to non-equilibrium effects. So in some way, they can be used to diagnose the transient ionization from observations. This is the solar point of view. If we go towards actually now to the fusion application, I'm showing you how to use the same model, so the same transient model, but in a tokamak diverter. So what you see here is actually exactly what I showed you at the very beginning. Is the bottom part of the tokamak, so just the diverter, and the first two plots for this panel and this panel are just the temperature and density, calculated by a model called scrape-off layer plasma simulations to derive this value. And from this value, using the transient modeling, and actually equilibrium and the transient modeling, I've calculated the ionization balance for helium line emission, for helium neutral helium and single ionized helium. And so, as you can see, there is, and obviously in the transient, this is just one specific time, and I use the time that is called time Elm. Elm means edge localized mode, so it's an instability that make the plasma be transient within the diverter. You can see that the ionization balance actually behave differently if we treat this with modeling, an atomic modeling, which includes only equilibrium, ionization balance, and atomic modeling that include the transient ionization balance. And the application of that, in the case of a tokamak, obviously is very similar to what we do in the solar atmosphere. So we need an line ratio to actually derive the intensity within to derive the temperature or the density within the device. And actually this is again shape of the diverter, and this is a diagnostics as a UV, or actually in this case visible, and these are the line of sight. So what you see actually in the panel down is the intensity summed along all of these line of sight. The green one is the one in the middle, while this other cross means that starts from the bottom. Oh, sorry, the bottom of the diverter. As you can see, this is an example of helium-1. And the two lines actually, these two actually has the emissivity of one of the two lines of the 6,680, and show a different behavior if we treat the emissivity along the line sides, the different line sides, in the case of equilibrium, non-equilibrium. So all of this point is the summed emissivity along each of those line of sight. So when actually we apply this to the two lines, for example, these two lines, a 6,680 angstrom and 7,283, which come from the singlet and are good for density diagnostic, we see that the ratio would be different, especially in this part, which is more active, if we apply the two models. And obviously this is important because the effect of transient of an emission along the selected line of sight would affect the density measurement. And so in conclusion, we actually, what done here, I try to use a common transient modeling and apply it to the solar flare case. And this is what you saw actually at the very beginning, application on solar flare from the solar maximum emission. And the modeling for the simulation of the master super Excel upgrade. Here actually I've shown the helium single ionized, just see actually the application for the other ion. So what you see here that we got the same transient plasma model, but applied to different temperature, density, and time scale regime. Specifically, the time scale, if you see here in the fusion domain is very small, we talk about microseconds, while for the solar we talk about seconds and actually seconds here, you can see. So to summarize everything, the main message is that all plasma information, so most of the plasma information are in the radiation, are in the spectrum. But obviously, extracting them and try to understand them needs a careful modeling. It's not so straightforward. First of all, the transient plasma effects, as well as the equilibrium approach, are both needed and are both required to actually confront the model with experiments or with theory or with observations. However, there is a problem here. The response of emission of a finite density environment and the transient can be very similar. So it is crucial, it is really important to actually treat them, model them together in our theoretical modeling to avoid misinterpretation. And obviously, because the new spaceborne instrumentation and the new laboratory device entail continuous development also from the theoretical point of view, to avoid interpretation error and to fulfill also the mission requirements. So the main message here is that we got quite a big synergy between solar physics, specifically the solar atmosphere, and the quantum fusion, specifically the tokamak diverter. And this is quite important because these two fields, these two environments can give actually mutual support and validation. So managed to finish. Thank you very much for listening, even with the stops.
Thank you. Very nice. Does anyone have any questions? So one question I had was, is there, you spoke a little bit about some of the assumptions that are made, zero density, ionization equilibrium, and optically thin plasmas, and then you spoke about that they are not always valid. So I wonder if we think about the optically thin assumption, that's often not the case in the solar atmosphere, right? Especially in the lower atmosphere, the chromosphere. And I wonder, can tokamak plasmas help us in any way there, or do we need to look to different laboratory experiments?
In the tokamak, quite often it's optically thin. Mm-hmm. So we don't really apply the optically thick modeling, but obviously that's not the case with the solar atmosphere. So, for example, for the helium problem, the chromosphere emission really need to use optically thick or almost thick emission. So I don't actually, at least for jet and for MAST, I'm not aware of any optically thick emission for the plasma, from the tokamak plasma.
Okay. Anyone else? Okay, if not, thank you again for the talk, and thanks for keeping returning when you get kicked off.